In this video, I would like to consider a static analysis of a two-dimensional rigid body. The first thing we want to do in any static equilibrium problem is to determine the body of interest. Consider the problem shown here. The figure shows a horizontal beam that is supporting an external 4 kilonewton load. The beam itself is prevented from moving due to a set of supports at points A and C. In this particular problem, we wish to determine the magnitude and the direction of the forces at points A and C. These forces are termed support reactions. The support reactions and the external load all act upon the beam, which we then isolate as the body of interest for this problem. With the body of interest determined, the next step is to classify the loads and supports that are acting on the body. There is an external 4 kilonewton point load acting at point B. The beam is supported by a pin joint at A, and the beam is also supported by a strut at point C. The strut at point C is an example of a two-force member. This means that the line of action of the reaction force is defined by the geometry of the strut. For this particular case, the line of action of the reaction force passes through points C and D. The next step in the process is to create a free body diagram. We do this by redrawing the body of interest and placing it within a 2D Cartesian coordinate system. We then add to the diagram the external loads and the support reactions that are defined by the problem at hand. The problem under consideration has an external loading which is a 4 kilonewton point force. The pin at support A produces a general reaction force. This force has both a magnitude and a direction and can be represented on the free body diagram as our Cartesian vector with components AX and AY. The two-force member produces a reaction force at point C. The magnitude of this force, FCD, is unknown, but the direction of its line of action is specified by the problem geometry and is at an angle of 45 degrees from the horizontal. At this point in the solution process, the directions of the unknown forces AX, AY, and FCD are not known. It is standard practice to assume a direction for these forces on the free body diagram. While it is a matter of preference, I typically always assume positive directions for all unknown forces. The last step in the process is to include on the diagram information that specifies the location of the forces with respect to the origin of the Cartesian coordinate system. With the free body diagram completed, the next step in the solution process is to develop the equations of static equilibrium. For a two-dimensional body, static equilibrium is achieved when the body is constrained such that the net force acting on the body is zero and the net moment calculated about any point in the two-dimensional plane is zero. This condition can be expressed mathematically by stating that the sum of the forces in the x direction equals zero, and that the sum of the forces in the y direction must equal zero, and that the sum of the moments about a specified point must also equal zero. For any given problem, these equations are written based upon the physical situation that is described by the free body diagram. For the particular problem being looked at here, we can write that the sum of the forces in the x direction is equal to AX plus FCD times the cosine of 45 degrees, and that the sum of these two forces is equal to zero. The sum of the forces in the y direction is equal to AY plus FCD times the sine of 45 degrees minus the 4 kilonewton applied load. The sum of these three forces must also equal zero. The last equation, we can take the sum of the moments about point A. While it is true that we could sum the moments about any of the points on the free body diagram, by summing the moments about point A, the two unknown forces AX and AY have moment arms that are equal to zero. This then yields an equation with a single unknown force, FCD. At this point, we can note that we have a set of three simultaneous equations that contain three unknown variables. Thus, the problem is well defined, and a set of equations can be solved to yield numerical values for the unknown reactions. The solution to these set of equations is quite straightforward. The equation for the sum of the moments about point A can be solved directly for FCD, which is shown to have a value of 11.3 kilonewtons. With the value of FCD known, the other two equations can be used to determine the values of AY, minus 4 kilonewtons, and AX, which is minus 8 kilonewtons. At this step in the process, it is now necessary to report your solution. It is critical to realize that the free body diagram is an integral part of the solution and must be included. The solution is presented here, shows both the free body diagram and the numerical answers for the unknown forces AX, AY, and FCD. The signs associated with the numerical values for the forces indicate their direction with respect to the direction of the force vectors given on the free body diagram. The negative signs present in the values for AX and AY indicate that the actual direction of these force vectors is opposite to that which was shown on the free body diagram. While it is standard practice to leave a solution in this form, many students often have a problem interpreting the physical meaning of the solution. When this is the case, it may be useful for the student to include a supplemental free body diagram that uses the problem solution to redraw all the force vectors such that their correct magnitudes and directions are clearly indicated. When this is done, the vector describing AX can be reversed and it can be assigned its magnitude of 8 kilonewtons. The vector describing force AY can also be reversed and it can be assigned its value of 4 kilonewtons. And lastly, force FCD, which has a value of 11.3 kilonewtons, can be broken into its Cartesian components. With this supplemental diagram completed, it is usually much easier for the student to verify that their answer makes physical sense. As a summary of the solution process, one should start with a careful reading of the problem statement. The information in the problem statement should be used to generate a free body diagram with unknowns clearly labeled. The free body diagram should be used to generate a set of three equations that describe 2D static equilibrium. The solution of these equations plus the free body diagram yield a solution to the problem. And lastly, a supplemental diagram can be used to assist in the interpretation of the solution and to help verify that the solution does indeed make physical sense.